I'm having two problems with my Kubota L2501 tractor. The first problem is annoying, and that is the tractor would start easily, run strong at first. I'll be working for quite a while at 2,000 RPM, but then I'll need to get off the tractor for a few minutes to do some other job. I would lower the throttle to idle, about 1,200 RPM, and then 3, 4, 5 minutes later, get back on the tractor, try to throttle up to 2,000 RPM, and it wouldn't do it. It acted like it couldn't get fuel. No matter what I did, shift to neutral, try the throttle up and down, nothing would work other than just waiting. So a few minutes later, the tractor would eventually get back to 2,000 RPM, and I could continue doing my work. Well, this problem has a workaround. I just leave the tractor at 2,000 RPM, get off, do my job, get back on, good to go. Problem 2 is a showstopper. Once again, the tractor starts easily, it runs very strong at first, and I can get 30 or 60 or sometimes even 90 minutes out of it. And then the RPM starts dropping on me. Sometimes it'll drop abruptly from 2,000 to 1,500, and I am done. I cannot get it back to 2,000. Other times it'll stutter a little bit. It'll go 2,000, and it'll drop a few hundred, come back to 2,000, might go through a few cycles of that, and then finally goes to 1,500 and stays there. At that point, can't do anything with the tractor. I can barely limp back to the barn. Now, in both cases, it acts like fuel starvation. So I am going to look at the fuel pump first and see if that might be the problem. I started with internet research to see what other people have found and what solutions they came up with. And I saw mixed results. I saw on some forums a lot of people with the same problems that I have. And their solution was to replace the mechanical fuel pump, with an electrical fuel pump. However, this was not a universal problem, as I also came across many people who said they've had that mechanical pump in their tractor for 10 or more years and it's been flawless. So it sounds like a problem that it's well known, but not universal. And I think the best approach for me is to try putting an electric fuel pump in and see if that will solve the problem. So that's where I'm going. I want to trace the fuel path from a tank through my system. So it comes out the bottom of the tank into this hose. This hose comes over here into my fuel filter. Now this fuel filter has a spring-loaded valve here. So when we take this bowl off to change the filter, this spring-loaded valve shuts off the fuel supply. Now after changing the filter, there's going to be an air pocket in this bowl. So when you put this bowl back on, the air escapes through this hose, and this hose goes back up into the top of our tank. Here's where the fuel comes out, goes through this long arced hose into our mechanical fuel pump. Now that's a cam-driven pump. It operates at about 1 psi when the engine is at 2,000 RPM, according to what I've read. I don't have the gauges to verify that. The output of this fuel pump comes up here to this bleeder valve. So behind the bleeder valve, the fuel goes into the injection pump. This hose is connected to another hose back by the injection pump, which is very difficult to see here, but it comes out right here and then goes back to the tank. And this is the overflow hose. So when the engine is at full 2,000 RPM under load, most of the fuel goes into the injection pump. When you drop down to an idle, it'll have excess fuel, and that excess fuel is returned to the tank through that hose. This is the fuel tank on our L2501, and this is the part we see when we lift the hood. But this is only the top part of the tank. The tank continues around behind the firewall and comes all the way down to here. Now, the problem with this design is that it's really difficult to inspect the tank for debris and clean it out. You know, it's fairly easy to see this part, but going past this angle, very tough. And I wish there was an easier way to do it. I've tried an endoscope, but when I put my endoscope down there, I either see blackness, or when it gets close to the wall, I see a glaring reflection, and I just could not get it to work to inspect my tank. So I don't know what's down there, and secondly, I don't know how I'd clean that. Here's the top view of our fuel tank. And one thing you'll notice is that this is a vented cap. It's not just a dirt cap. You can actually pry this piece out. There's a small black foam behind it. I checked that right away to see if that was clogged up, and it wasn't. But look at all the dirt around here. I mean, it's a tractor. So you have to wonder, is fine dust getting into my tank, and over a period of time putting a film of sticky dirt at the bottom of that tank that could be partially obstructing the fuel outlet? Well, I just don't know. I could not get an endoscope to work. Now, people have suggested that you take the fuel sensor unit off to have a larger opening. This will only come off if you tilt your fuel tank forward. Otherwise, it hits the firewall and you can't get that large flange off of there. This is also a better view of the return hoses. This is the return hose from the top of your fuel filter. It's primarily a return hose for air. This is the return hose from your injection pump. So if your fuel pump is providing more diesel to your injection pump than the injection pump is using, the excess fuel is returned here. So I think the best place to mount this electric fuel pump is right here in this opening in front of the firewall. So I'll take some preliminary measurements and see what kind of bracket I might need to make that work. So there's a rough idea. It's a simple bracket to make, so I'll go ahead and make one and see how well it works. This is how I start to make the supporting bracket. That piece of steel is 3 inches wide and 1/8 inch thick. So I transfer the roughed-in measurements I obtained by holding a tape measure in that opening by the firewall, lay the pump and optionally a relay on the steel, mark it, drill it, cut it, weld it, and then sand the edges smooth. Here is another view, and you can zoom in on the square to see the dimensions I used to make this bracket. I made several brackets to see which one would fit best. And that's pretty easy because once your tools are set up, these only take a short while to drill, cut, weld. This is my first one. It bolts to the firewall right there using the existing Kubota bolt. The pump is mounted here at a 45-degree angle, as nearly all the manufacturers recommend. And I put a hole here so I can either put an automotive relay or an eye bolt to zip tie the wires to. This is a pretty good design, but I decided it'd be better if I removed this excess steel. So here's my second design. Steel's been removed. That's the Kubota pump. There's an eye bolt to zip tie the wire to. Now, I tried some other pumps and they fit a little better with a drop down there. Now, the good news is that these pumps seem to have a very similar bolt hole spacing. So this Facet Posiflow pump and this Kubota pump are interchangeable in terms of the bolt holes. Here is the factory bolt on the firewall where I want to put the bracket and fuel pump. So this bolt, it's an M8 by 16, but I'm putting a bracket on there that's 3 millimeters thick. So what I'm going to do is try some slightly longer bolts. So there's the factory 16 millimeter. Here's a 20 millimeter. Here's a 25. I'm surprised that when I put the 25 in there, it did not bottom out. So that's the one I'm going to use. Here is the dry fit of the bracket, just to make sure I have good clearance in all directions before I go ahead and mount the pump on it. I'm still dry fitting, but this time I put the pump on it and it looks like I have clearance all the way around. So I'm going to continue with one more dry fit, and if it looks good, I'm going to finalize it. This is the Kubota pump. Here's my final dry fit. I put that plastic guard back on and everything fits with good clearance. So this is the design. I'm going to finalize it. I'll take it apart, paint it, put it back on permanently. Here's the final mounting of the fuel pump. The reason we only need one bolt to secure it is because this bracket is sitting in the lip of that firewall. So between the bolt and the bracket, this pump assembly is quite secure. Here's how I'll route the fuel lines for this new pump. So starting at the filter, the current line comes over here to the mechanical pump. I'll disconnect this line, shorten it, and put it right here on the input to the electric pump. And this will have a very gentle radius through its entire length. Currently, the output of the mechanical pump is right here, going to the bleeder valve and the ejection pump. I'll take this line off, get a new section of fuel line that runs from here up and around with a very gentle radius to the output of the electric pump. Now this radius is a little tight, so I have to be very careful that I don't pinch my hose. When that's done, the mechanical pump won't have any lines on it anymore. So what I'll do is take a short section of fuel line and just make a loop from the input to the output. If this electric pump works the way I want it to, at some point I will take this mechanical pump off, fabricate a blocking plate to put on in its place. Now let's get technical about pumps. So for the D1703 engine, Kubota provides these numbers for us. At 2000 RPM, we are consuming about 1.4 gallons per hour of diesel, and that matches my on-the-ground experience. Now, when I looked at pump catalogs, even the smallest pump easily satisfies the 1.4 gallon per hour requirement. So that will not be a factor in our pump selection. So let's move on to some other characteristics of these pumps that we need to consider. When we start looking at catalogs of low pressure fuel pumps, we'll come across two types of technology most often. The impeller type of pump is the one that is usually placed inside of a fuel tank. It has very low self-priming lift, so that kind of limits where it can be placed at our engine bay. A better choice for us is a solenoid pump. And these come with a wide range of PSI, wide range of gallon per hour. But what's very helpful is that they have a self-priming dry lift of 12 inches or more, 24 inches, 36 inches, or even higher. So this gives us a lot of flexibility in terms of where we place it in our engine bay. Now we still want our fuel to be gravity assisted to go into our pump, but we don't have to be at the very bottom of the tank for this to work. Now the aftermarket prices vary widely. For the premier manufacturers, for a pump that would work for our L2501, is going to be typically $70, $80, or $90. Now that's an aftermarket price. This shows the basic operation of a solenoid fuel pump. This is a field effect transistor that acts as an on-off switch. When it's on, current flows into the solenoid, creating a magnetic field, and that magnetic field causes this plunger to be pushed towards the input port. And as it's pushed towards the input port, it compresses the spring and also pushes this input check valve closed so fuel can't be pushed back into the fuel tank. This plunger assembly is hollow, so the fuel in this region is then pushed through the middle of this plunger. That opens the output check valve, and fuel then goes into the injection pump. Now when the field effect transistor turns off, the magnetic field collapses. This spring pushes the plunger back into the solenoid. And as it does that, it closes the output valve and opens the input valve, so fuel is drawn from the fuel tank back into the fuel pump, ready for another cycle. Here is another inside view of a typical solenoid fuel pump. It does show the input check valve very nicely. This plunger tends to be a one-piece unit, and the check valve for the output port fits in the end of this plunger and is held in place with a circular clip, a circular spring clip, something like this. I'm sure each manufacturer places slight variations on their own pumps. This is what the current draw on our fuel pump would look like on an oscilloscope. So you see these sharp spikes of current when the solenoid is turned on, and then down here the solenoid is turned off while the plunger is being pushed by the springs. So we continue this cycle: solenoid on, push the plunger into the springs, solenoid off, springs push the plunger forward. This 1.4 amp average draw is for a typical pump, but you can see it is not a steady state current flow like you might have in a regular motor. It is a series of pulses on and off. The fuel pump manufacturers always recommend 45 degrees as the best angle to mount these pumps, with the inlet at the bottom. They usually say that vertical is acceptable and horizontal is acceptable, but 45 degrees is optimum. Now there are a few reasons for this. One is the vapor elimination. If you have very hot fuel in here, any kind of vapor forming, it readily has an escape path. The other big advantage is that there is always some residual fuel in this pump, so it's primed and ready to go. And the third reason is that this seems to be the optimum angle for the springs and the check valve to work in this pump. We can't slap any old fuel pump onto our tractor and hope that it works. We need to look at the specs and see if we can make an educated choice as to which pump might be best for us. So the example to start with are these two Facet pumps, and Facet is considered a very good brand for fuel pumps. This pump has the lowest specs I could find in their big catalog, and I think these specs might be comparable to the mechanical pump that we're replacing. But of course, we're replacing that pump, so maybe we don't want to go quite this low. This PosiFlow pump is one that I often see recommended for diesel engines in the 25 to 50 horsepower range. So looking at these specs here, this PSI range, 2.5 to 4, is called the deadhead PSI when no fuel is flowing. So that's your maximum static PSI. Now, its maximum flow rate of 30 gallons per hour only occurs at 0 PSI. So these two numbers have to be balanced with each other. And then you get a typical flow of 5 gallons per hour at 2 PSI. Well, the 2 PSI sounds really good. The 5 gallons per hour is quite a bit higher than the 1.4 gallons per hour that our Kubota engine uses. So we'll probably get a little less flow at perhaps a slightly higher pressure. But if you go to 2.5 PSI, that seems like a very reasonable pressure for our tractor. Now the dry lift is the self-priming, and 60 inches here and 40 inches here, those are both really good numbers. That means we don't have to mount these fuel pumps at the very bottom of our fuel tank, because there's enough self-priming dry lift that we can easily draw fuel all the way out of our tank. So here are the pressure versus flow rate for these two facet pumps. Now this deadhead of 2.5 to 4 PSI only happens when there is 0 gallons per hour flow rate. And then this free flow of 30 gallons per hour only happens when there's 0 PSI. So somewhere in this range here is where we get the operating pressure and operating gallons per hour. Our Kubota L2501 is about 1.4 gallons per hour. So if you come down here to 1.4 gallons per hour and come up to, let's go to the PosiFlow pump, we're going to be right about here. So somewhere around 3.25 PSI at 1.4 gallons per hour. Now if you go to the smaller pump, the same 1.4 gallons per hour, we see 1.5 PSI. Those are both good numbers. So it looks to me like both pumps might work. Since we own a Kubota tractor, we have to wonder if there are Kubota fuel pumps that would work for us. And the answer is yes. And here are two examples. So the first one is widely used in the BX tractors, but it's also used in excavators, wheel loaders, mowers, and others up to about 50 horsepower. But there are concerns with this Kubota pump. The first one is that Kubota does not publish specs. So we don't know the PSI and gallons per hour and dry lift. When you look at the aftermarket pumps that claim to be compatible, these are the numbers that they usually publish. So it is in the range that should work for us. The other problem with Kubota pumps is that they're very expensive. This pump will be currently at a dealer over $200. The aftermarket pumps that claim to be compatible will be 1/2 or 1/3 that price. When you cross-reference this pump, you'll find that it's used in 59 Kubota machines. Not just BX tractors, but also front mowers, garden tractors, excavators, and others. And when you start looking at these machines, they go up to 50 horsepower. So this pump is a reasonable choice for an L2501. When I told my local Kubota service manager what I wanted to do to my L2501, he recommended this pump. Now this pump has the same problem as the other pump in that there are no listed specs from Kubota. When you look at the aftermarket pumps that say they're compatible. The PSI in gallons per hour and dry lift look like a good match for our tractor. And of course, the other problem is the Kubota pump will be quite expensive. The aftermarket pumps that claim to be compatible will be 1/2 to 1/3 the Kubota price. But it is a genuine Kubota pump. When you cross-reference this Kubota RD411 pump, you see that it's used on a lot of different machines. And what gets our attention right away is that this is the pump that seems to be used on a lot of the larger L series tractors. So this is a pump we definitely have to look at more closely. Here is the RD411 pump used on an L2501 tractor. Well, you can't get much closer to an L2501 than an L3301. So I think this might be a really good solution for a Kubota branded pump. And even though I don't know the specs and the price is high, I did go ahead and buy one of these, just trusting the Kubota reputation for quality. Here are the 4 pumps we've tested. The 2 facet pumps with the detailed specs, the good price, and the strong reputation for quality, and the 2 Kubota pumps with no detailed specs, a high price tag, but a reputation for good Kubota quality and reliability. So what do we do? Now, this is by no means a comprehensive list. There are many more pumps that might work in our tractor. But to narrow it down, my choices are this Facet 60248 and this Kubota RD411. I think those are the 2 most promising pumps to try on our L2501. Now, one good thing about these pumps is that they have the same bolt spacing. So if you are not happy with one of the pumps, you take it off and the other pump fits in exactly the same bracket. For the electrical, there is an existing 10 amp circuit on our tractors. It is right here, and it's called work light. So what I'm going to do is tap into that and use it to either drive the pump directly or to drive my automotive relay. The work light that we want to tap into is on the inside of the left rear fender, and as I zoom in, that's the connector that we want to tap into. That 10 amp work light circuit has wires that come out under the left fender. And you can see under the left fender here where the wires come out. And this work light is right here. It's a T connector, and that's what I'm going to tap into. I'm going to test this work light connector that comes out of the rear fender. So with key off, it shows 0 volts, which is what we want. And with key on, it shows 12.5 volts, so it looks perfect. Now, looking at this work light connector itself, it's a T connector, and looking into it, it has female spades. The top of the T has a yellow wire, and that is the positive. And then the vertical arm of the T, if you look at it like an alphabet letter, the vertical arm is negative, has the black wire coming out of it, and that is confirmed in the voltmeter. Now, I have to make a decision about the wiring. That work light wire would be sufficient to drive the fuel pump by itself, but it doesn't have enough current capacity to do anything else. However, if I put a bank of relays here, regular automotive relays, that work light circuit could easily drive this bank because they're typically only 20 milliamps each. So I could have a relay for my fuel pump fused, a relay for my forward facing high intensity lights on my ROP, relay for the high intensity LED lights facing rearward on my ROP, and then a 12-volt circuit to drive a pump on my 3-point sprayer. So this is the way I want to go, but first I'm going to focus on getting the fuel pump working. And if that's working satisfactorily, then this will be a follow-on project, and it'd be quite easy to take the wires that I have on the work light circuit and bring them over to this bank of automotive relays. Here's what I had in mind for using a relay bank: to use this one work light circuit not just to drive the fuel pump, but as a control signal for a bank of relays. Now each of these is only about 20 milliamps, so it can easily handle a bank of relays. So this relay would go to the fuel pump as an always-on situation. And then, for example, this relay could go to my front ROP lights, this relay to my rear ROP lights, and this relay to an auxiliary 12 volts. And all of this is coming directly from the main 12-volt battery. The work light is just acting as a control signal to select one or more of these circuits. Here is a schematic drawing of the previous slide. These are just standard 4-pin automotive relays. They are rugged and durable and inexpensive. Here's the wire I'm putting together to go from the work light connector to the fuel pump. I'm using marine grade wire, which is tin coated copper, so it won't corrode. And here's the T connector. I made a practice set first, a male and a female practice set, just to make sure I was doing everything right. And I didn't have a crimper that I thought would do the job for me, so I did it the old-fashioned way. I'm also using the red and black wires because that's the same color as the wires on the Kubota pump. Here is the Kubota fuel pump with the completed wiring. The Kubota pump uses a red and black wire scheme, and I've kept that same red and black wire scheme going back to the work light connector. So here is a T connector. The red and black wires go through a protective split loom. This goes behind the bracket and then goes through an existing opening in the firewall. That opening also has the tachometer cable and the throttle linkage, but this wire that I've added doesn't interfere with either one of those. There's plenty of clearance for all three. Here's the new wire for the fuel pump coming through the firewall right here. This is the throttle linkage, and whether I'm at minimum throttle or maximum throttle, it doesn't even touch this split loom. This is the tachometer cable. It also does not touch the split loom, so there is plenty of clearance here for the throttle linkage, the new wire, the tach cable. Nothing is rubbing, sticking, or binding. This wire now goes between the fuel tank and this pedestal, which holds the instrument cluster and the steering wheel. And there's a nice little space here that makes this wire go through quite easily. Here is the new pump wire on the left side of the tractor. Here's the fuel tank. Here's the pedestal that holds the steering wheel and the instrument cluster. Here's my fuse box, which is starting to get pretty worn. The label's getting pretty worn. And here's that wire. There's actually a nice amount of space here for this wire to go through without any pinching or binding or resistance at all. So the wire goes down here, and I have it zip tied to some existing wires. all the way back to the rear fender. Here's how I'm bringing my new wire from the fuel pump back to the work light connector under the left rear fender. There's a space between the fuel tank and the pedestal for the instrument cluster, and that's where I'm bringing the wire from the fuel pump on the right side of the tractor over here to the left side of the tractor. And then the wire inside this protective split loom is routed along this existing wire, like you see here. It's a very neat, very clean solution, and it goes all the way back to the left fender. My new wire continues back towards the inside of the left rear fender. Here's the new wire. It's zip tied to the existing wire. Comes behind the ROP right here. And then it has this T connector to the existing work light. I left this loop large for this illustration, but I'm going to go ahead and zip tie this up a little bit tighter under the fender so it has better protection. Time for a quick test. So I have the key in ignition, but it's off. When I momentarily turn key on, if this is connected properly, we're going to hear a rapid ticking sound. I'm only going to do it for a second because it's dry, but I do want to make sure before I go any further that the wiring is correct. So here we go. Sounds wonderful. Here is the fuel line all attached, and I'm using SAE J30R9 hose. So the hose comes out of the filter here, and I used the same simple spring clamp that Kubota had on the factory hose. So the hose comes out of the filter, works its way up here into the bottom of the fuel pump, and that had a long barb on it, so I went ahead and double clamped it. The top outlet of the fuel pump, double clamped, and Kubota used these screw clamps on the pressure side, so I did the same thing. Makes this radius, which is a little tight, but I think it's okay. Comes down here, goes into the bleeder valve. Behind the bleeder valve is the injection pump. I only had room for a single clamp here. Now on the existing fuel pump, the mechanical pump, I just took a piece of the old hose and made a loop around here from input to output. If this electric pump works as well as I hope it does, at some point I'll take this mechanical pump off, fabricate a blocking plate, and put the blocking plate and a gasket on there permanently. To prime my pump for the first time, I disconnected these clamps temporarily and made sure that gravity would fill this line with diesel fluid and any trapped air would be pushed out. And then I put the clamps back on, opened the bleeder valve, and also took the fuel cap off so I could listen to return fuel coming in. Turned the ignition switch to on position, but not starting it. And after just a few seconds, I could hear the fuel return line doing its job. I could hear fluid, I could hear diesel coming back into the fuel tank. At that point, I closed the bleeder valve, started the tractor, started beautifully. Well, it's running fantastic, and I didn't put the split loom on the lines just yet because I want to watch these for several sessions just to make sure I have no leaks or seepage or any other problems. But this is really encouraging. Now what I've got to do is run this under load for a few hours to see if I really did solve that problem. Here is the tractor put back together again. Everything fit just great. It is a very clean install. I am very pleased at how it goes from an idle back to 2,000 RPM. This is one of the big problems I had before. It would struggle to get to 2,000 RPM. And now it does it smoothly and easily. And to me, this engine sounds a lot better than before. Back to a good workhorse of a tractor. Been running this for quite a while and none of the heat soaking problems that I had before. So I think that fuel pump was very worth the time and cost to put it in. I hope this video was helpful to you, and I hope it works for your L2501 as well as it works for mine.